out of the Lending Foundation. Next week we'll be in Peter Jones 116 for our statistics and scientific writing lab. And after that, the week after that, it's like November 1st is the first week of independent projects. We have essentially like about a month in which to do your project, and we can talk all about how you think it's going to work for you to do it in your experimental design. And this bird watching activity tomorrow is it's hopefully your first chance to sit down and think about what your project might look like. As you're pulling up my neon green binoculars and looking at birds. All right, today we're going to talk about life histories and competition. We will wrap up this idea of life histories here at the beginning of class, and then hopefully get into this idea of organisms interacting with one another in what we classify as competition. We're ready to start talking about how, not just how populations grow and change over time, but how populations interact with each other. And we're going to start by looking at it from what we call intra-species competition, what happens when individuals of the same species compete with each other. That will be our first couple of lectures on competition. And then we'll expand that to look at what happens and how we can quantify competition between individuals of different species. So we're going to talk about trade-offs in reproduction and life history patterns at the beginning of class today. And then we're going to start talking about intra-species competition. And our elk here, which are competing with each other for mates, is a prime example of intra-species competition. When organisms of the same type compete with one another for limited resources. Cool. This idea of competition feeds directly into our population growth models and distributions of populations over space and time, because competition is one of these density-dependent factors that influences population growth. And we'll talk about how that actually works out, like what happens to individuals when you have high competition and how that then relates to population growth control. So all these factors are intertied. All right. We had looked at this slide in class on Tuesday, and we were starting to talk about reproduction, and we had all these different population growth models and different things that were happening. And then we said, okay, the thing that is driving population growth is reproduction. And how an organism reproduces, when it reproduces, how many babies it has when it reproduces affects population growth. Okay, it's those life history qualities that affect population growth in addition to age structure and gender ratios. And in general, if everything was perfect, the best strategy in order to make more of yourself so that you would get more resources and win competition for resources would be to make as many babies as you can, as often as you can, as soon as you can in your life. Okay, and that is true in certain environments, and for what we're going to call our life history strategists, this strategy is the best. But in the real world, there are constraints, and there are differences, and there is competition, there is predation, and there are random factors that happen in the environment. And so doing as much as you can, as early as you can, as often as you can, sometimes is not the best strategy for your perpetuation of your own genes as an individual and for the perpetuation of your population from a species perspective. And so some of the things that constrain this early, often, fast strategy are things like limited resources, your particular phylogeny and taxonomic history. It is not in your genes to make 500 babies at a time, like you won't. Your particular environment and these species interactions, competition and predation, these density-dependent factors alter the best overall strategy and give us a gradient of what species actually do. Okay, so we talked about asexual and sexual reproduction, and that those are the two base strategies, and now we're going to start making that more complex. And we talked about not only asexual and sexual reproduction, but what are the advantages and disadvantages to that? And there are trade-offs, and they're kind of the opposite of each other. And so in different situations, asexual reproduction will be great, and then sexual reproduction will be helpful. And for many species, they swap between the two. And they have a life history strategy where in a portion of their life cycle, they're asexually reproducing, they're making spores, they're budding off colonies, and in other parts, they go through a sexual phase. And so they play both strategies against the middle in order to get benefits of both. The other thing to remember in reproduction and in understanding these different life history strategies is to recognize that there is a trade-off in reproduction. If you want to pass on your genes, if you want to grow your population, you have to reproduce. But it's not a freebie, okay? There is a cost to reproduction. And when you reproduce, how often you reproduce, how many babies you make, has to be balanced with that cost of reproduction. And so one of the things that has to be balanced is the fact that reproduction often increases individual mortality, okay? Your resources that you place into reproduction reduce the resources you have for your own survival, okay? And so this is the data that's shown here. We're looking at red deer populations, I think that were in the United Kingdom, and they're looking at the mortality rate, those QX column in the life table, that happened between milk hinds, so female deer that had a calf, and yield hinds, which are female deer that did not have a calf. And so at any age, which is what the little tick marks are, female deer that have a calf have a higher mortality rate than if they were not attempting to raise a calf. Those resources that you put into feeding a baby, protecting them, moving around, getting resources for yourself so that you can feed your calf, come at a higher mortality risk. And so you have to balance, am I going to reproduce now and put myself at a greater risk of death, which means that I won't be reproducing at all in the future if I die, versus the benefits of reproducing. Okay. And again, if you don't reproduce at all, you're not passing on your genes, but you maintain the chance that you can reproduce in the future. So there has to be a balance between that. And you start to see that as these deer age, the mortality rate goes up, again, regardless of whether or not they have a reproductive effort in that particular year. And this is, again, where you start to recognize that these deer need to have reproduced by this age, or else they're going to get too old to have a deer or to have a calf. Okay. And so, again, when to reproduce starts to become apparent that you've got to do it sometime here. But if you do have a calf, you put yourself at a greater risk for dying yourself. Okay. The other thing that tends to be true for organisms is that putting in a reproductive effort now reduces your fecundity, reduces the number of offspring you can have in the future. And again, this is a resource cost, that by putting in resources to offspring now, you will have less resources for offspring in the future. And so again, how many offspring are you going to have now means that insured, I'm having babies now, but I might not be able to support these babies in the future. And so how am I going to divide my resources? Am I going to put everything into reproducing now as much as I can, knowing that I will not have any more babies? Or am I going to do a little bit now and a little bit next year and a little bit in the future? And that has to be balanced too with this idea that if I reproduce, I have a greater chance of mortality. Okay, here again, we see in terms of these red deer, if you have a baby this year, your fecundity, percent of fecundity, how many of them have a calf the next year, is less than if you didn't have a calf this year. Okay, if you didn't have a calf this year, regardless of the deer age, you have a really high chance and percentage that you'll have a calf in the future. But if you have a calf now, especially early on or late, you have a really reduced chance that you're going to have a baby in the future. And part of this is because you're putting resources into that offspring, which means you don't have resources in the future. And part of this is because you're really likely to die if you have a baby now as a young deer or as an old deer. Okay, and that means you won't have any babies in the future if you die now. Okay. It also holds true in plants, and so lots of the examples we're going to be talking about for competition and predation. I try to have a vertebrate animal example. I try to have a plant example. And to me, that's important because it helps us to recognize that this data and these trends are true across phyla of organisms, that this is a constant thing that we see in ecosystems. Here they took pink lady slipper orchids, which are these beautiful plants. They're relatively endangered in lots of places across their geographic range. And they artificially pollinated them to make sure that they would have either less fruits and seeds that they produced or more fruits and seeds that they produced. And they found that in lady slipper orchids that produced more fruits in one year, they had a lower probability of flowering in the next year. Okay, there was a cost to reproducing a lot now. It meant that they would not produce as many offspring in the future. Whereas if they didn't have any seeds and fruits this year, they had a higher probability of reproducing the next year. And this was across different sizes of plants. And so the other thing they found, of course, was that the size of the plant definitely played an effect on their ability to support fecundity, and it played into their growth rate in coming years. If they didn't produce any fruits, they had more resources for reproduction and growth in coming years. And that's the third trade-off that comes with reproduction now, is that it affects individual growth. Okay, and that you have to balance your reproductive effort now with your ability to grow in the future. And again, for many organisms, this is a resource division, and that the energy I don't put into offspring now means that I can grow bigger, which means that I have a better chance of surviving and can produce more offspring in the future. But I have to balance that with the fact that I might die between now and my next reproductive effort and not get a chance to pass on my genes. And so again, organisms are constantly acclimating to their environment and adjusting to current conditions. At the same time that their particular life history shows an evolutionary adaptation to balancing reproduction and resource use over a long-term particular type of climate and ecosystem interactions. Okay, and in this case, these organisms, both in our conifer trees and in our fish species in the bottom, show this balance between passing on genes now, how much they reproduced in a given year in terms of gametes produced or in terms of number of cones produced versus their growth in the future. And so we see that in these conifer trees, if they made a lot of cones, they did not grow as much as conifer trees that didn't make as many cones, had a much higher annual growth rate. Okay. The same thing happened in the fish. If they made a lot of babies, okay, their growth rate was less. It's like the axes are flipped for these two. But if they did not make many babies, they had a higher growth rate. And again, this is important for organisms because bigger generally means better reproductive effort. And so again, they have to balance, do I pass my genes on now versus can I grow bigger and do better and survive better and reproduce more often in the future? And for different organisms, the answer to that question is different. And that depends on your life strategy, on your life history and your environment. In general, as I've mentioned, bigger is better when it comes to reproductive effort. And so you want big organisms to be reproducing because they're able to have the most resources to put into reproduction. This is definitely true in organisms like our fish species and our plant species. What we see here is data for vermilion snapper, which is a rockfish, very like red snapper and gray snapper that lives in the Gulf of Mexico and around the Caribbean islands. We can see that as the fish get bigger in length, they're able to produce more offspring. And it's orders of magnitude more offspring. Okay, like a lot.
Yeah.
Okay, we're talking about 10 inches of difference, and we're talking about like 2 orders of magnitude difference in the gametes produced. Okay, this has real consequences for our population. And that you want your fish to grow and live long enough to be making lots of babies. That's how you maintain your population. It's also really important for conservation efforts and for fishing regulations. You actually want to set a size limit for your population that says you can't keep the big fish you catch. Those biggest fish you catch, you want to go back into the population because they're doing most of the reproduction. They're the ones that are maintaining population size. You also don't want to catch fish when they're too tiny to the point they haven't even reached sexual maturity yet. Okay, but you want to eat these fish because they're doing less than one of these big old fish. In general, for populations, why is bigger better? And it comes down to size, and that the bigger you are as an individual, the more resources you can put into making offspring, the bigger buffer you have acquired. The other thing that tends to be true for most organisms is that they get bigger with age. And with age, not only comes more resources available to them, but they have more experience. And so this is particularly true in things like mammal species, and in some types of reptiles and amphibians where parents are engaged in raising the offspring. The bigger they are, the older they are, more experience they have raising offspring. It's not uncommon in things like big cats and canines, in bears, that the first couple times an organism reproduces, all the babies die. Like, they just don't know how to do it. They don't know how to feed them. They don't have a good territory. They haven't established a good pack relationship or mate relationship that allows them to be successful at this. And then their second or third try, like, they now know what's best, what not to do, what predators to be on alert for. They have chosen a better mate, better partner, and they do better. And so again, size often equals better reproduction effort, more success. Okay. The other thing is that size being linked to age means that if you have survived to be big and old, your genes are probably more fit for that environment. Okay, you haven't got picked off. And we want those most fit, most well-adapted genes to be passed on to the next generation. Okay. Here again, we're looking at crabs, 3 different species of them. We see that as the female body weight increases, the number of eggs that she produces also increases. The same thing happens in these cute little squirrels. Regardless of what habitat they're in, as they get older and they get bigger, and if the biggest ones at the same age definitely are able to raise the most offspring. Okay. Size equals good competition for resources, which means that either because you have more resources or because you have the knowledge and experience or the genes to get more resources, you'll be more successful at survival. Okay. That means that you should delay reproduction, right? Okay, like in a perfect world, hard, fast, soon, lots is good. But in terms of bigger being better, that means you should delay reproduction until you can get big. And so we have these two things that are at odds with one another for reproductive success. The idea that reproduction now benefits you in terms of passing on your genes, but there's a cost for reproduction to future survival, reproduction, and growth. And the bigger you are, the better reproduction will be, which takes time. And so we see that organisms constantly are balancing these different impacting factors for reproductive effort. Okay. When we ask about the timing of reproduction, then we're thinking about the age of sexual maturity, when a particular organism is going to be capable of moving from pre-reproductive age classes into the reproductive age classes. And from the data that we've just seen, delaying it until you're bigger should be the best scenario, because then you will be able to make more babies, you'll be more successful at it, you will pass on more of your genes. But there are always caveats, and there's always this balance in evolution, in competition, in predation interactions. It turns out that we see that the age of reproduction tends to be earlier in organisms reach sexual maturity at a smaller body size and sooner after birth if they're more likely to die as an adult than as a juvenile. Okay. And this is because your long-term survival is low, okay? Or I should say, your long-term survival is good as long as you can make it to being an adult. Okay. And so they tend to reproduce early if they're more likely to die as an adult than as a juvenile. You have to go hard, fast, soon, or else you're going to die as an adult. So do that. Okay? Don't wait to get big and make lots of babies. Do it now fast, because you aren't going to get to be big and make lots of babies. Okay. If you're more likely to die as a juvenile than as an adult, then wait with sexual maturity and reproduction until you're big and able to make lots of babies. Okay? A bunch of you are going to die before you even get to reproduce. But if you can live long enough, you'll make lots of babies. And so the two things are balanced. We have, in the case of early reproductive effort, lots of weak little babies that are likely to die, but we have some genes that are passed on. It's balanced by a lot of you are going to die and only a few of you are going to reproduce, but you're going to do a lot of reproducing once you make it to survival. And overall as a species then, the reproductive survival comes out to be about the same. Okay? And they end up being balanced for each other. And there are different situations when these two strategies are best for that environment, or for best for the interactions that are happening. What we saw with these little guppies in the experiment that's in our textbook is that they took a population that was experiencing adult predation. And so they were having lots of early reproduction because the adult predation rate was high. And they took these fish and they put them in a pond with high juvenile predation. They switched the timing of predation. There were different predators. In the first pond, where the adults were getting eaten, they had a bigger fish that was eating bigger prey. And they put them in a pond where they had a smaller predator that was eating smaller prey, the juveniles. And when they took this adult predated population that had early reproduction, they saw that they shifted to the delayed reproduction effort. They saw that they had delayed sexual maturity, that they decreased the resources they put into early reproduction in order to be able to grow bigger. This resulted in less offspring that were produced because they had to wait longer, but each offspring was bigger because they got more resources. And so it's an adaptation to that predator. If that predator is going to take lots of small prey, it's to your advantage to grow to a size where you can make big babies that are less likely to be predated upon. And it takes longer to do that, and you're going to make less babies. But overall, the same number are going to survive than if you make a whole bunch of babies that get eaten or die really soon as soon as they get big enough to eat. Okay. So it's always this trade-off, it's always this balance. Cool. Okay. We end up with these two general life history strategies then that we call K and R. And K-selected species tend to be like our juvenile predated species that are delaying sexual reproduction. Our K-selected life history strategists tend to invest in large, well-developed offspring. They tend to give a lengthy gestation period and lots of resources to each offspring. They have really heavy to moderate parental care offspring. They're really invested in making sure those fewer number of offspring survive. They tend to incubate offspring. They tend to have internal fertilization when it comes to sexual reproduction. Their strategy is to put a lot of resources into just a few baskets, but make sure those few baskets, those few offspring survive to adulthood. K-selected life history strategists tend to be long-lived and have late maturation, somewhere in the age, of 3 to 5 years, and sometimes it's even longer than that. In humans and elephants and whales, in lots of the primate species, organisms don't reach sexual maturity until they're 7 to 15 years of age. Okay, that's really long in comparison to our life history strategists, which can take 6 weeks and reach sexual maturity. Okay. They put in lots of energy investment per young, and as such, they can only raise a few offspring. And they must reach a big enough size, have enough resources at their disposal in order to raise well those few offspring. Definitely examples of K life history strategists are sharks and stingrays. All of our marine and large land mammals fall into the K life history strategists. Elephants, primates, humans, bears, they're all K life history strategists. They reach sexual maturity relatively late. They have few offspring at a time, but they take really good care of those few offspring. They're playing the long game. And that their slow, steady reproduction that's relatively assured will keep their population numbers high. They have big bodies and long life expectancies so that if conditions change, they have a resource buffer in order to be able to wait for positive and good conditions. Karen.
So does this have something to do, I've seen whales carry their dead young, their young die.
Yeah.
I feel like that kind of increases mortality with your fish, and you pop out a bunch of eggs and they're just floating and you're not like, ew, they're out there.
Yeah.
And then you have a young calf that dies and you're worried about that one thing.
Oh yeah.
And you have more investment in feelings, and that's where.
Oh yeah. And so this is a trade-off in that if you invest a lot, it's likely your offspring will survive. But if that offspring fails, you put in a huge effort that really affects your survival and mortality, your future fertility negatively. The other strategy is like, throw them out there and who cares? I can make more. Okay, and that's honestly the two strategies, and it works in different situations. If you have a pretty stable environment where you can count on conditions and resources, it's to your advantage to get old, to get big, to put a lot into offspring. If conditions are totally random and very chaotic in your environment, you're better off viewing them to the wind and hoping somebody survives. And that way you have ensured that you can survive to try it again. And it sounds heartless because we're human and we have consciousness and we view this as heartless. It's also clear that in some cases, particularly with both primates and cetaceans, the big whales, that it looks like they do have true emotion. And that's something that's a recent recognition. But they do go through this breeding process, even in elephants, some of our big land mammals, for offspring that they have lost. And there's more than just this reproductive effort, gene passing on, breeding gene hypothesis that's out there. And that complicates it. Okay, the flip side of this are our life history strategists then. They invest in as many small offspring as they can, and they make those babies as soon in their life as they possibly can. They're that classic, go early, go often, go fast. The consequence to this, though, is that they have really high mortality rate of offspring. And for many of them, they spend all their resources in one or a couple reproductive efforts. And then they die because they have spent all of their resources in this massive reproductive effort. Our selected life history strategists, and again, they're kind of defined by their per capita growth rate, little r here. K life history strategists are so named because their population size is really dependent upon carrying capacity for their environment, which is K. Our selected life history strategists tend to be these broadcast spawners that release gametes to the environment, and then they have external fertilization, where males and females can be widely separated from each other. And because of that, it's hard to rear offspring in that environment. And so they don't make an effort to do that. It's not worthwhile in terms of offspring survival and their own future growth as a company. Their strategy is often called in the mini basket category, that we're going to put a little bit of effort into a whole bunch of baskets, and a few of them will survive. And so the end result is the same. You can only make a few baskets, but a few of them survive. Or you can make a lot of baskets, but only a few of them survive. They tend to be really short-lived as a species with very early maturation of, I have 1 to 3 years on here when we're talking about fish species like these little anchovies. But it can be weeks when we're talking about mammals and insects, to go from egg to larvae to sexual reproduction. Is this making sense to everybody? I know Madison may have seen some of this before in environmental studies. Okay. In this R versus K life history strategy, then we can see that they have almost the opposite characteristics for lots of different traits. And that R life history strategists tend to be opportunists. They tend to have very variable population sizes. They experience exponential growth. In terms of population growth curves, and then they experience population crashes. They're opportunists in that if conditions are right, a lot of their babies can survive and their population will increase rapidly. But then, because they're opportunists, they'll overeat, they'll overuse, they'll go way past carrying capacity, and then they crash down to low population sizes. So they have really variable population size limits. Our life history strategists tend to be small bodied. They don't grow very often, very much before they start to reproduce. They never get very big because they get eaten. Because they're prey. Our classic prey species are rabbits, our mice, our insects, our small fish species, our invertebrate mollusks, the things that eat primary producers and then themselves get eaten. Those are classic R life history strategists. And because they're likely to be eaten, they have early sexual maturity, and they have lots of babies at a time because there's not going to be many chances for them to reproduce. Okay. And as such, they have a short life expectancy and high adult mortality, and so it's to their advantage to reproduce as early and as frequently as they can. But because their life expectancy is short, they generally reproduce 1 or 2 times, which is what we call a seminal parity. If they live long enough, they can reproduce lots of times, but most of them don't. And many times these species only go through 1 or 2 reproductive cycles before they're supposed to die, because their reproductive effort of making so many offspring is so resource intensive. And so a salmon is the classic example of this, where the salmon grows and then it makes this huge migration in order to spend all of its resources getting back to the perfect environment for it to produce its offspring. And then it does that once and it dies. Okay? You never see the adult salmon coming back down the stream to the ocean because they die in the stream. They're an RLF history strategist. Even though it takes them 3 to 5 years to reach sexual maturity, they make lots of offspring. They only do it once. They have really high adult mortality. Everybody dies. As such, they have low energy investment per offspring, and their population growth is really density independent, in that they're really sensitive to changes in their abiotic environment, because that determines resources and thus how many offspring have their children. All right, the opposite of this are the K-life history strategists. They tend to be what we call stables. They maintain stable body size, stable body temperature, stable population size. They are in environments that tend to be very stable over time, and if there are changes, they live long enough that they can withstand those changes without big consequences to population size. They tend to be big. They tend to be predators. They tend to make just a few offspring at a time, but give them really high energy investment and lots of care. And again, high energy investment is always relative to the RLF history strategists, which do none. And so even guarding eggs, as in the case of an anemone fish, or as in the case of an octopus, counts towards this K-life history strategy, where there's just more investment per offspring, even though you might be guarding 100 offspring at a time. Your resource investment there means that you can only make 100 offspring at a time instead of 1,000. They tend to live longer. They tend to have high juvenile mortality, but once you get to an adult stage, then you have a longer life expectancy. And because of that long life expectancy, even though they're only making a few offspring at a time, they're going to get that chance to reproduce many times. And that's what we call iteroparity. There are going to be many iterations of your reproductive cycle. And they tend to be defined in terms of population size by density-dependent interactions. Competition, predation, toxic waste buildup, disease tend to influence carrying capacity and thus how big their population is going to be. K-life history strategists tend to be much more sensitive to human impacts on them and their environment, because their reproductive success and effort is low because they're only making a few offspring at a time. And so if you take out just a few breeding females from a K-life history strategist population, you can really change reproductive effort. Whereas if you take out a few mice, the overall population production is not going to be terribly impacted. So life history bleeds into how the population is going to grow and change over time, and it bleeds into conservation and population management, as well as expectations of what that population is going to do in terms of interactions with their environment. All right. Hopefully, I've laid this out in this beautiful little scenario of R versus K. Most species are not perfectly R or K. Most species have some strategies and characteristics of both. And again, our canine species are good examples of this, in that wolves and dogs have a really early sexual maturity. They have a medium life expectancy, 8 to 10 years. They're going to make a relatively high number of offspring each time, like 5 to 7, but they're going to do a fair energy investment in each offspring, but then they're going to do it every year. Okay, and so they have some traits that are K, and they have some traits that are definitely R, and they can go through big population explosions, then they overpredate, and then they go through population crashes. And so it turns out that this type of scenario is helpful in looking at evolution and these trade-offs in reproduction and longevity. But most species are playing both strategies against the middle, and they're what we call periodic life history strategists. And they've got some traits of both. And the tarpon here, which is this big, long-lived ocean-going fish that makes 1 billion eggs at a time, is a periodic life history strategist. It's K in terms of body size, trophic interactions. It is R in terms of reproductive effort. You can go the other way too. You can have short-lived organisms that take really good care of a few offspring in order to help them survive. Like that could be a strategy too. Periodic life history strategists tend to be aggregate or nest spawners. Lots of times they do have external fertilization, but then they're doing a little bit of care for those eggs. Okay, so again, the anemone fish is an example of this, where they're going to reproduce frequently. Like every 6 weeks, they can have another set of eggs. But they're doing like 50 and 100 eggs at a time, and they're actually taking pretty good care of those eggs. Once they pop out of the egg, ready for the next batch. And so they're showing strategy a little bit of both. Modest energy investment for something that we can't classically place as art. Tarpon, salmon, tuna, birds, big, long-lived, but they can make lots of babies. That's a periodic life history strategist. In your textbook, it talks about R, C, and S life history strategists for plants. And that's a similar system when it comes to this idea that some plants grow and reproduce in 1 year, and that's it. That's an R life history strategist. Some plants, like our trees, grow big and grow old and are going to want to do a little bit of reproduction every year. Some are going to be just kind of eating. When resources are abundant, they'll do a big reproductive effort, but then next year they might not have the resources, so they won't reproduce. Those are like stress tolerant. There's the periodic. All right. Again, in terms of an evolutionary perspective, the goal here is to win resources so that you can pass on your genes, so that your population can be the biggest in that particular ecosystem. And so we have these different strategies that are trying to win. If you make a lot of babies, you can really dramatically increase your population and get more resources in the future. But you're really prone to just being blown out of the water by something random that happens. If you wait, you can ensure that a few of your offspring are going to live, and you can keep picking away at getting more and more resources generation after generation. But you're really open to that fast-growing species coming up underneath you and grabbing resources away. If you're a K-life history strategist, you're sticking it out, but you might get outcompeted. But you're going to win competition in the long run. If you're a periodic guy, let's try to put together the best of both of these strategies. As I said, you might make lots of baskets, but you're going to have an opportunity to make lots of baskets in the future, okay, rather than dying early on. Or you might take care of some offspring to ensure that some survive, but each time you're going to make fewer offspring. Okay. All right. It is interesting, in light of R and K life history strategists, and to think a little bit about the human population. And that R life history strategists tend to show these exponential growth curves and then population crashes. K life history strategists will grow to carrying capacity, and then they'll bounce around near carrying capacity as conditions and predation and interactions change. Humans are classic K life history strategists, but our recent population growth has been clearly exponential. And so, what does that mean for us? It's concerning. There's a strong potential for that. And economists And mathematicians have been predicting a population crash for humans for a solid century, if not a century and a half. They've kind of been looking at resource use and changes in quality of life and the longevity of humans increasing, and been concerned that we're outpacing our resource production. And they predict famine, and they write crazy stories about eating babies, right? Which are intended to be crazy, but also make you think about what's actually going to happen in the future. But that hasn't happened, right? Like, we've been talking about it happening. We've been predicting it to happen in every next 10 years, and it hasn't happened. And so that's very interesting too, in terms of humans as a population and our own population growth and what carrying capacity for humans might be on the planet. And so this is data again from our textbook, and we can look back in the past and we can kind of estimate what human population was like in the past, looking at millions of people. It took us until about 1800 to get a billion people on the planet. We didn't get, kind of the second billion people until the start of the 1900s. And then all of a sudden, we've added 4 billion people in the last 75 years. And we've had this exponential growth of the human population that's been enabled by real changes in modern medicine that have changed and enhanced life expectancy, and modern agricultural practices, which have expanded our nutritional resource base. So technology and medicine have allowed for an exponential rise in human population. The big question for demographers of humans and epidemiology, sociology, conservation biology is, when and will we level off? When will the human population hit its carrying capacity? And have we overshot it? And by how much? What will it look like? How will we know that humans have reached carrying capacity? Maybe I'll ask you guys that question, turn to your neighbor and say, how will humans know when they have hit carrying capacity?
We can't finagle things anymore. So we have to.
Yeah,
we can't find anywhere for our trash to go, or anywhere for our waste to go, or
not have enough food for everybody.
Not having food for everybody.
Yeah, that's a definite sign.
Environmental effects like smog and the reduction of carbon dioxide in the air, pollution.
Sure, this buildup of waste again. When we talk about biocapacity, we think of both resource production and also waste removal. And remember that those things are things that control or density dependent that limit population growth. So based upon those factors that you just outlined, have we hit carrying capacity? Do we have enough food for everybody?
China doesn't, apparently.
Depends on where you're looking.
Right, exactly. And even here in the tri-state area, we think that somewhere between 25 and 30% of all people experience some type of hunger during their lifespan. Whether it's chronic hunger or it's just malnutrition, it's a particular point in their life when they couldn't get access to enough calories or the right kinds of nutrition. It's already apparent that we are not doing a good job of distributing our resources, particularly when it comes to food. That some people have enough, some people have too much. Clearly, some people don't have enough, even here in the United States, regardless of sub-Saharan Africa, which is where the hunger issue is probably the worst. What about waste production?
We don't find a way to get rid of our poo and our trash, and where is it going to go?
Right.
It's already going into the ocean.
Right, exactly. It already goes into the ocean. It already goes and gets in places we don't want it to go. We're already sending it in places, in terms of the United States, we're already sending it to places that have been taking it. Actually, China has stopped taking our trash.
But they have to because of the contract.
Right. Yes, so they do have some contracts they have to fulfill. But China is making this move towards more environmental sustainability, and the first thing they did was they told the rest of the industrialized world, you can't send your trash and your recyclables to us anymore. which means that now we're finally having to actually deal with the waste that we produce. This is definitely a problem in terms of CO2 production and methane production, that we are at the point where we have filled up the buffer that the ecosystem had for our burning fossil fuel and plastic production consequences.
So if China's so good at doing that, then why isn't everyone trying to get into that practice of whatever they're doing with the trash? Why isn't everyone trying to do it?
So now because China was doing it cheaper than what we did in the United States. So of course, we have to pay for that. Even with the shipping, it was cheaper to send it there. And so now we have to take their technology and build it here.
Right.
And so
With
actually
people that don't want to do it, want to do it for more money.
yes, exactly. And it'll be more expensive because we have higher wages and we have more regulations they have to adhere to. And so it'll be more expensive. And that's hard for communities that want to deal responsibly with their trash and have been. Now that's going to be a greater economic burden. And are the customers, are we willing to pay for that? And we're all going to answer differently. And some communities are like, yeah, like let's do this. And let's put in an extra tax and let's build this facility. The problem is this time period between when it's piling up and when the facilities get built. And the other big problem is that because we've been doing recycling okay for a couple of decades now, we have flooded the market with recyclable base materials. And other industries have not got the capacity to build those recyclable materials in. So we can recycle plastic. No one's buying the recycled plastic pellets. And so it's not a profitable business model. And so there's a couple things that have to change in the economy for recycling to rebuild itself here in the United States. And in China, it was a system where we sent it over there. They did it cheaply with cheap labor and poor environmental regulations. And then they sold it to their companies that were making us the plastic stuff. And then they shipped it back to us as formed plastic. Like they had the thing, it was going there. And we don't have anybody here in the United States that's building stuff out of recycled plastic because it was all used to be happening in China. And by China, I'm talking about like any of the Southeastern Asian countries. There's a swath of them that have been involved in the Texas. And so it's like, it's hard. It's not a simple fix. And it will take time. And in the time that we're switching, in the time that we're regearing, in the time that we're rebuilding, the waste builds up. And communities lose a taste for doing it at all.
Yeah, I feel like, oh, I'll be dead by the time, or it's not my problem. I hear that all the time. It's like a domino effect, though. Like it's like when you're trying to change one thing, it's going to change another thing that's going to affect these people, so they have to change, and they have to change something. It's just like dominoes.
Yeah. We did this native planting thing this weekend with my environmental studies class, and I took my kids this time. And so we planted all these plants, and they were all like totally pumped about it. And then we get in the car, and my kid was like, my one son was like, but we saved that place. But then like there's this gas station, and we're driving on the road, and there are all these houses, and he's like, what about all that stuff? And I was like, yeah, it's a problem. And you could just tell that he was like, oh my God, there's this big problem. And then he was just like, I don't know how to fix it. And I was like, you don't have to fix all of it. Okay, there is a balance.
If everybody does a little bit of something, then it definitely helps. It might not obviously save carrying capacity, but what we've been doing. So we keep figuring out these new ways.
Right. And it's more than just individual changes, which help. Every change helps. It is getting the appropriate big companies to change as well, because they have a bigger impact. Their buying practices, their production practices do the things then that we're asking for. And so if the company starts using more recyclable materials in their packaging, there will be a market for more recyclable materials. It will get cheaper and easier to recycle again in the United States. But it all has to be linked. It is a domino effect. And we have to figure out the right pressure points in the system. We're reaching the pressure points, the tipping points, in terms of our natural ecosystems and human population and carrying capacity. How we deal with that and the actual impacts of it are really open to the choices we make today. It's clear that we've been putting off making these decisions about lifestyle choices and recycling, waste production, fossil fuel use for several decades. We've known about these problems and we have not really changed activities. How many of us there are and what we all do in the future is going to be a really big impact. In that, do we have a population crash for humans? I certainly don't hope so. I do think that population growth rate is slowing, and the human population growth rate has been slowing for a couple decades now. We just have a big population that continues to grow because there's a lot of people, even though we're reproducing much more slowly. Total fertility rate, I may mention this on Tuesday, total fertility rate for humans as recently as 1965 was 5.5 babies per woman, and it's now globally 2.3. Okay, like that's a halving the population growth rate. We just have 7.5 billion of us. So we're going to add more, but we're starting to level up. We're reaching that point. It just really depends upon our ecosystem and our resources that are available in reproductive rates as to do we end up at 10 billion or do we end up at 8 billion? Do we have a drop? Crash before we do. Right. Those are real questions. And like they're our questions. Okay. Like you will live to this 280. Okay. You will see this happen one way or another. I just realized that like when 2050, I'll be like 70 years old, and I'm just like, oh, it won't matter anymore for me. But I have kids, and they'll be like 30, so
You want them
or 40.
You want them to like live a nice, healthy
Yeah, exactly.
life, not like experience drastic famine and.
Right. Like I read a lot of science fiction, and I'm like disturbed. Right.
Okay, zombie apocalypse.
Exactly. This is like a real problem. It has not helped that my kids have started reading The Last Kids on Earth, which is about these like junior high kids that survive
Like monsters. and
Yeah,
stuff.
yeah. Now my kids are like, I'm building my treehouse in my go bag in my like closet, and I'm like, this does not help my anxiety at all. And they're like, you need to build us a treehouse so we can be safe from the zombie apocalypse. And I'm like, I know.
I know, you have to take me. If I build it, you have to take me.
And I keep being like, your dad and I will take care of it. I don't want my kids to be like hoarding food in the closet, right? But at the same time, I'm like, it's nice to know there's another stash somewhere.
Get the Twinkies.
Yeah, I'm like, don't forget the chocolate. All right. So we've covered population growth. One of the things that really influences population growth are species interactions. It's one of these density dependent factors. And it comes down to the fact that organisms share limited resources. And they come in all shapes and sizes. There could be abiotic resources and there could be living resources that organisms have to share or that they have to gain sole access to. And the main mechanism that we see in which organisms are interacting is in competition. So we have lots of organisms in the picture here which are competing for a variety of different resources. And so it happens across all types of species. It happens within a species, and it happens between different species that share a very similar ecological niche or that share a food resource or habitat resource. Okay, so competition is the first of these species interactions that we are going to talk about. And we can define competition as when one organism uses a resource at the expense of another. Okay, we have two or more individuals that are attempting to use the same resource at the same time. And that's competition. I think it was last night at the dinner table, I was like, oh, we're going to start talking about competition finally in ecology. And my son was like, oh, you mean like in sports when there's like competition for like a prize or like winning a race? And I'm like, kind of. But the things that we're competing for are different than prizes. The prizes have a different quality to them. And again, it's intra-species, I-N-T-R-A, if the competition is between members of the same species. So we have two anemones here which are competing with each other for space and essentially access to food resources that comes along with that space. And so the anemones will sting each other in order to drive others along. Corals, which are very similar Cnidarian species to anemones, corals will actually eviscerate themselves, their guts will come out and they can digest their neighbor corals in order to feed them back in competition for space. There are some phenomenal Blue Planet time lapse videos of corals like battling each other for space on the coral reef. Cool. That is really cool. Interspecies competition, INTER, is when we have members of different species that compete. And some types of competition are specific to within a species. There's lots of overlap in intra and interspecies competition. What they're competing for are limiting resources. Resources that are scarce relative to the abundance of this organism's, the population itself. A limiting resource is one whose scarcity limits population growth, that sets carrying capacity for a population. So what would be some examples of limiting resources?
Space.
Space,
Mates.
mates, food,
Shelter.
shelter,
Territory.
territory, good. That's pretty much it, okay? And again, you've got these abiotic things. You have shelter, access to clean water, access to light, space, and then you access to mineral resources. And then you have these biotic interactions, food, mates, territory. And for any given species, we can look at particular competitive interactions, but they're competing at all of these different levels all the time. And so again, we can define a best strategy, and then we wonder why all species don't show that same best strategy. Well, there are trade-offs, okay? Just like there are trade-offs in life history strategies, there's trade-offs in competition. And making yourself good at one thing might open you up to competitive areas in other arenas, or might open you up to predation, or might make you more susceptible to disease. And so there's going to be these trade-offs that we see as organisms specialize or generalize in terms of competitive goals. And the differences in competition lead to speciation over evolutionary time. Competition is one of the main driving natural selective forces for evolution.
Are those two anemones seeing each other right now, like trying to?
Yes, they are. Not mating. It is entitled Clone Wars.
Yeah, it's on Clone War. So it's like that's like literally its offspring, but it's just a
It
little
could be.
too close, and it's like,
Yeah.
hey man, back it up.
Yep, and like we talked about, one of the disadvantages of asexual reproduction is that your offspring very often end up right next to you, and they compete with you for those basic resources that you're also trying to get. Hopefully, if one of you dies, it's still you that lives, but there are less of you. Okay, so things that individuals vie for within a species. So again, we're going to talk first about within a species, and then we'll expand this to between different types of species. Within the same species, individuals fight with each other for resources, for food. This can be really problematic, even for high density plants, right? Like plants are vying for basic resources of moisture and light. The same abiotic factors that we measure in the environment are these limiting resources for organisms. They set the carrying capacity and the level of competition. Individuals of the same species fight with each other for space, okay, for access to shelter and for access to food that comes with that space ownership. Okay. A great example of this are fish in a pond. There is a limited amount of space in that pond in which you can exist as an individual. There is limited space in that pond where you can nest and lay eggs. There's limited space in that pond where you can hide from predators. There is limited space in that pond to provide food resources. Individuals within a species also compete for mates. And so the mate competition is something that is unique to intra-species competition. It only happens in members of the same species, right? That's what defines a species, is that you can interbreed to produce fertile offspring. The level of mate competition comes in a whole variety of different things, but In essence, you're trying to show gene dominance in your competition for mates. Whether it's males choosing females, females choosing males, it kind of goes all ways in terms of sexual selection that we'll get to talk about throughout the semester. But again, in Songbirds in Spring with their displays, they're trying to show that they have the best genes, and thus their genes are most adapted to the environment by having the biggest, longest called, most brilliant feathers, the best nest building space. And thus mating with them means that the offspring will have the greatest chance of survival. Okay. The biggest male is showing gene dominance by being big, by having gotten lots of resources. So if you mate with me, your offspring will get more access to resources. There will be more of you in the future. And so it plays into these life history characteristics and traits, these competitive displays, and the things that organisms compete for influence life history traits. Life history traits influence competition. Okay? We want it to be this straight line and make these real easy connections, but it's a tangled web of complexity. Okay, all right. There are several distinct types of competition that we can observe in the environment. And the first of them is what we call scramble competition, or a scramble response. And in scramble competition, all individuals of the population are affected equally by the competition, by the interaction. And so, in essence, growth and reproduction are usually depressed for all of them when competition is high. Okay, that's a scramble response, when each individual is scrambling for resources. And the more individuals there are, the more competition, the greater the impacts on an individual and a population scale. So an excellent example of a scramble competition and a scramble response are large herds of herbivores grazing. The more grazing there is, the less there is for everybody. But each individual is getting the resources on their own. Okay. That's a scramble competition, a scramble response. No one individual of the herd is more or less impacted by the actual interaction. And in fact, lots of times in scramble responses, we see that exploitation competition is taking place. So we're going to see scramble and contest competition as our two types. And exploitation is one of these mechanisms or subtypes of this competition. And in exploitation competition, the individuals in the population interact indirectly with each other. They're not, because they use a resource, then they exploit that resource. It's not available for anybody else. But it's not like they walk up to the zebra and like bump them off the great grazing pasture. They just eat the good grass and then it's not there for anybody else. They've exploited the resource. And in doing so, they indirectly compete with their neighbor. Tree roots and gaining access to moisture is definitely a scramble exploitation competition scenario. Each individual is competing on their own. When they take up the moisture, then it's not available for their neighbor. The more trees there are, the greater the competition, but it's not like the tree roots are like fighting each other underground. Okay, although they do some cool stuff with compounds that they can release to inhibit root growth in neighboring plants. But it's not, that's exploitation scramble competition. Everybody's depressed equally. Okay, nobody wins more than their neighbor. Everybody suffers if there's a high density. Does this make sense to everyone? Okay. The flip side of this, the other type of competition from scramble is what we call contest competition or contest response. And this is where some individuals win. Okay, some individuals get more resources in the contest for resources and others suffer. Not everybody is equally affected. Some win and have enough and others are denied that resource and they have less. Okay. This means that growth and reproduction in contest competition is only depressed for some individuals in the population. And again, the denser the population, the higher the abundance, more individuals will be left out. But some will still get enough, and some will win, and some will reproduce and grow just fine. And in a contest competition, it's really to your advantage to be the winner of competition because you will have enough and your offspring will have enough. You are likely to survive and reproduce again. And those that lack have a lower reproductive and survival rate. Okay. Very often in contest competition, we see direct interference competition, where individuals interact with one another directly. Okay. They defend a territory. They fight aggressively for mates. That's our interference contest competition. Again, the male ibex here that are fighting for dominance over a herd, that's aggression interference contest competition. Whoever wins that direct interaction will gain access to reproductive rights. Whoever loses is out of luck. And they might even die if they've spent too many resources or been injured in the contest. Kleptoparasitism, in which individuals of the same species steal resources from other individuals of the same species, is a type of interference contest competition. And so in our two little plover seabirds here, sand shoreline birds here, we have one that is going to steal the food kind of right out of the mouth of the other one. That's kleptoparasitism, where you're acting like a parasite by stealing from your own species. If you steal the nesting site of your neighbor because it's better, that's kleptoparasitism, which I just think is a great word. If you build a barrier to resources, that means that you have access to the resources within it and your neighbor does not. That's a form of direct contest competition. That's territory defense. If you're going to say the resources in this area are mine and I will defend them, that means I have access to them and you don't. The last one here is what we call cryptic interference. It's on this gradient, I would say, between exploitation and interference competition. If your mechanism of competition is that you avoid members of your same species so that you don't enter into direct competition with each other for resources, that's still competition, okay? If the way that competition manifests itself is that you avoid each other so you don't have to fight each other, that's still competition, and that's avoiding a direct conflict in order to then be able to both win contests for resources. So this is territory defense in things like big cats, where they're loners. And they live alone and they actively avoid members of the other species because they know if they get into a fight, they're going to hurt each other and they're likely to die, both of them. And so they have cryptic interference where they do kind of everything they can about marking territory, laying out kills in order to say, this is mine, don't come in. You stay over there, no problems. The only time they come together is for mating purposes and for raising of offspring. And the rest of the time, it's cryptic contest interference competition. Cool. Does that make sense? All right. Tuesday, we'll pick up with the consequences of intra-species competition. Guess what? It affects mortality. It affects reproductive effort. It affects growth rate. Just like the balance between reproductive effort and longevity does too. Okay, but we'll have examples of that and how competition affects growth rates and survival and fecundity. Cool. And then we'll talk. The other thing we're going to do on Tuesday is talk about mechanisms. We'll get into territoriality as well as some other things like what actually does competition do to cause changes in survival and reproductive effort and growth rates. Okay, where are we meeting tomorrow? Valley View. You're gonna come here.